Hi everyone, welcome to the first video in this calculus series. Today I wanted to cover the fundamental idea behind why calculus exists and the types of problems it is used to solve. Let's start by establishing a motivation to learn calculus in the first place. Calculus has numerous applications in a lot of different fields. The rate at which medicine would be absorbed by the body is modeled using calculus, as well as determining the heat lost in an object over time. Calculus can also be used to calculate the volumes of irregular shapes and even solve complex physics problems. The two most important concepts in calculus aim to address the tangent line problem, or in other words, the rate of change of a function, and the area under a curve. Let's break in and address the tangent line problem first. Let's define what a tangent line is. A tangent line is, by definition, a line that only intersects a function or curve at one given point. Now the question is, how can we find the slope of this function at the given x equals 2? One approach would be to approximate this with a secant line. So what I'm going to do here is I'm just going to redraw this function. And I'm going to pick a point that is relatively close to x equals 2 in order for us to approximate what the slope of this could be. So I'm just going to pick a point P over here. And now I'm going to connect the 2 points with a secant. Now let's compare the slopes. What do we notice? We see that the slope of the secant is actually fairly close to the slope of tangent. It's just a little bit steeper. What would happen if we move point P closer to where x equals 2? Let me draw that out. We'll be able to see what actually happens here. So we have, here's our point at x equals 2. Now point P is really close. Ooh, that didn't necessarily touch, but you get the idea. Now our slope is really close to the slope of the tangent. So it seems like we can conclude something. As the slope, or as we move our point P closer to x equals 2, our slope of our tangent line, of our secant line, approaches the slope of our tangent line. Approaches is a key word here. Now I'm going to throw some calculus terminology at you. When we say that the slope of our secant line approaches the slope of our tangent line, we can also say that the limit of the slope of our secant line as point P approaches the point in question equals the slope of the tangent line. That's what a limit is. All right, let's write this out more formally. So I'm going to call this point O. So when we talk about limits, we write it out mathematically as lim, as P approaches O of the slope of our secant line would be equal to the slope of our tangent line. Another way of writing this would be lim as x approaches 2 of, now I'm just going to give you the slope equation, which would be x squared minus 2 over minus 4, over x minus 2. Now, to evaluate a limit, all you need to do is plug in the value that we're approaching. So if we try to plug in 2, here's what happens. We get 4 minus 4 over 2 minus 2. Do you guys see a problem with this? We get 0 over 0. This isn't good. This is what's called an indeterminate form. When you have a limit of this form, we need to perform some sort of manipulation in order to actually solve for a value. So let's try this again. I'm going to rewrite this limit. So we have the limit as x approaches 2 of x squared minus 4 over x minus 2. And let's try to manipulate this so that we don't get 0 over 0 next time. So from what I see, looking in the numerator, we can factor out a difference of squares. So I'm going to rewrite this, and we get x plus 2 times x minus 2 over x minus 2. And we have the same term on the top and the bottom, so we can cancel these out. Now you might be wondering, why can we do this? Shouldn't there be a domain restriction? Well, you'd be right, but that's what's special about the limit, as when we are solving a limit, we never actually reach the value. In this case, it would be 2. We're just approaching it. And having this limit here lets us know that we can never actually get to 2, but we're just approaching 2. We're getting really close to 2. So because of this, we're not actually violating any domain restrictions, and this is why we're allowed to just knock out these terms. So rewriting this, we now have the limit as x approaches 2 for x plus 2. And now this one's easy to solve. We just plug in 2 for x, and we get 4. This tells us that the slope of our secant line when x approaches 2 is going to be 4, which is also equal to the slope of our tangent line. This is the idea behind the derivative, but we'll get more into that in another video. Now we're going to talk about continuity. For a function to be continuous, it can't have any abrupt changes in value. The way I like to think about this is that the function must be drawn out by a smooth curve. If it fits this criteria, then it's continuous. Here are a few examples of continuous functions. We have y equals x cubed, which is continuous because it can be drawn out in a smooth, unbroken curve. And we have y equals absolute value x. This also fits the criteria because it can also be drawn in a smooth and unbroken line. Discontinuity is the opposite of continuity. Discontinuous functions cannot be drawn out in a single, unbroken curve and do exhibit abrupt changes in value. There are 3 types of discontinuities to keep in mind. The jump discontinuity, which is characterized by having an abrupt change in value at a given point. The limit at this given point does not exist. The next discontinuity is the infinite one, and it's when a part or parts of a graph break off to infinity on its domain. The last discontinuity is the removable or point discontinuity, and it's where there is essentially a hole in the graph at a given value. The limit exists at this point, but it is undefined in the range of the function. So I wanted to wrap up this video on some examples, but before I do that, I had one more point that I wanted to mention that I forgot to earlier. In order for a limit to exist, the limit from the left must equal the limit from the right. This is very important. There are many cases when the limit of a function at a given point just doesn't exist. You have to keep this in mind. The limit from the left must always be equal to the limit from the right. Alright, let's start with some examples. So for the first one, we have the limit as x approaches 3 for x squared. So what do? We can just plug in 3 in for this limit to evaluate. So we get, we get 3 squared, which is equal to 9. So this one was easy. Here we see that the limit as x approaches 3 of x squared is 9. Let's move on to 2. Here, let's try the same thing. Let's plug in the value we're approaching and see what happens. So here we're approaching 1. So what do we get? We do 1 squared minus 1 over 1 minus 1, which gives us 0 over 0. This is the indeterminate form I was talking about earlier. That means we have to try something else before we can actually evaluate this limit. So let's try it again. We have the limit as x approaches 1 of x squared minus 1 over x minus 1. If we factor the numerator, I see there's a difference of squares, we'll get the limit as x approaches 1 of x plus 1 times x minus 1 all over x minus 1. We see that we can cancel out the x minus 1 terms, which leaves us with the limit as x approaches 1 of x plus 1. Now I'm running a little bit out of space here, but we see that when we plug in 1, we get the answer to be 2. Therefore, the limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. For 3, this one is slightly different. We haven't really seen something like this before. When you see a negative sign over the number we're approaching, it means to approach from the left. If it were positive, it would mean approach from the right. This makes sense because if we look at a Cartesian plane, we see that the negative values are on the left and the positives on the right. So that's how you would remember this. Now, to evaluate this, when you're trying to evaluate a limit from one side, essentially what we're doing is we're plugging in a value really, really, really close to the value we're approaching, but from one side, in this case, from the left side. So we'd have negative 0.00001. So as we can see, this value actually gets really, really, really big in the negative direction. We can confirm these findings by drawing a graph of this function. So I'm just going to draw this out. And we'll see that as we approach 0 from the left, that we actually get really, really close to negative infinity the closer we get. So therefore we can conclude that the answer for this limit would actually be negative infinity. For the next one, the first thing I'm going to do is draw a graph of this function. So we know that from negative infinity to 0, non-inclusive, the function is x. So I'm going to draw a little hole at 0. And we have x. Now from 0 to infinity, it's x plus 1. So I'm just going to move up one unit and then continue the function. So as we can see here, we have what's called a jump discontinuity. This is where things get a little tricky. We have to evaluate the limit at 0. So this is where you need to check if the limit from the left equals the limit from the right. In this case, the limit from the left is 0, and the limit from the right is 1. This means that the limit does not exist because the limit from the left is not equal to the limit from the right. Therefore, the answer for this one is does not exist. And that wraps this video up. Give it a thumbs up if you liked it, leave a comment, and we'll see you when we talk about derivatives next. Thank you.